Okay, friends, welcome back. As I think I mentioned on Friday, we've got an exam coming up on Saturday the 27th. If you have University Accessibility Center accommodations, I have already incorporated those automatically as exceptions to the exam, so you should be fine. It's a 3-hour time limit, multiple choice, same format as last time. We won't get through all of chapters 7 and 8, and whatever we don't get through of 7 and 8 won't be on the exam. I'll have a better idea of what we will and won't get to as the week continues to progress. Other than that, I think we're ready to get going. So we were talking last time about potential mechanisms for reactions and how we might collect data to provide support for one mechanism versus another. And in particular, we were talking about a substitution reaction, and I forget what all of the details were. I think this was the particular example. But we were talking about the mechanism of substituting a cyanide group for iodide. We're replacing this group with this one. And we talked about thermodynamics and then about kinetics, and we basically considered 3 different possibilities. One was to make the new carbon cyanide sigma bond first, then break the carbon iodide sigma bond. We didn't really like that one. Our next option was to break carbon iodide first, and that would give us a carbocationic intermediate that would be high in energy. And then we said in a second step, we could, make the new carbon cyanide sigma bond. And then our third option was to do both at the same time. And we basically ruled out the first option because there's not enough space around small carbon for it to be bonded to 5 different things. But we consider both options 2 and 3 and what their consequences would be, what their kinetic signatures would be. And we sort of ended with, how are we going to know what's the appropriate course of action? And the answer is, well, molecules will take the lowest energy pathway available to them. And so we're going to learn some fundamental principles that are going to tell us whether option 2 versus option 3 are going to be chosen. Now, I'll just add that we said that option 2 is going to have first order kinetics in the methyl iodide and be 0 order in cyanide, because we said cyanide concentration doesn't affect the kinetics of this reaction. And we said that the reaction, the rate law that summarizes that is some rate constant times the concentration of methyl iodide. And because there's only one concentration term in this rate law, we said that the reaction was unimolecular. And we'll summarize all of this in a name for this mechanism, SN1, where the 1 stands for unimolecular, S stands for substitution, and N stands for nucleophile or nucleophilic substitution. So we're substituting a nucleophile for a group that leaves. So that's the substitution in the nucleophilic part. The 1 has to do with the fact that the rate law is unimolecular. Now there's a potential source of confusion that I want to talk about that gets people every time. The SN1 reaction mechanism, remember if we drew an energy diagram, you had starting materials here, a carbocationic intermediate here, and products there. And this reaction was 2 steps. So the 1 doesn't refer to the number of steps. The 1 refers to the fact that the first rate determining step only involves the methyl iodide. Okay? So we would call this mechanistic proposal number 2 an SN1 mechanism. And you should be familiar with all of these descriptors we've used for the SN1 mechanism. Question so far? All right, if we do both at the same time, we talked about how this mechanism would have no intermediate. If we were to draw an energy diagram for the making the new carbon-carbon bond and breaking the old carbon iodide bond at the same time, we would go through a single transition state without any intermediates, because both the new bond and the old bond are breaking and forming at the same time. Our rate law is going to depend on both the concentration of methyl iodide and the concentration of our nucleophile. The rate law is first order in methyl iodide concentration. It is first order in cyanide concentration, and it is therefore second order overall. There are 2 concentration terms in the rate law. And because of this, we'll say that the reaction is bimolecular. That is 2 concentration terms in the rate law. And so our abbreviation for this reaction is SN2, bimolecular nucleophilic substitution. A little bit more on the review. If we were to describe what the transition state looked like for the rate determining step, as we drew it last time, we would have the carbon iodide bond lengthening. We discussed how that can happen. It happens just by transfer of kinetic energy from one molecule to another that excites vibration of the carbon iodide bond to the point where the bond breaks. So the transition state would involve the iodide leaving. The intermediate is a carbocation. That carbocation in this case is just the methyl cation, but it's sp2 hybridized, and the key feature here is you've got an empty p orbital on the carbon. The carbocation is planar and may be attacked from either side. That will become important later on as we talk about stereochemical consequences of the reaction. I'm not drawing the transition state for the next step because it's not the rate determining step. It would simply involve a nucleophile attacking the carbon from either above or below. And if I asked you to draw an arrow pushing mechanism for this reaction, in organic chemistry, arrow pushing is simply the instructions for each step. Arrows that you have in the same drawing you communicate must happen at the same time. So to convey the fact that in the first step only the methyl iodide's involved, we would show an arrow like this, starting with the carbon iodide bond and ending with the iodide nucleus, to indicate that iodide leaves and takes its electrons with it. The intermediate would be the planar carbocation, like we drew above, and then I minus is the leaving group. And I suppose these 2 electrons, or any 2 of them, are the ones that used to be in this carbon iodide bond. Pay attention to the convention for using arrows in organic chemistry. The arrow must begin with either lone pairs or electrons in bonds. The arrow must end either with a nucleus or in the space between 2 nuclei to indicate the formation of a bond. And then in the second step, we would show our nucleophile CN minus attacking at the carbocation, at the positively charged carbon, to give us our new carbon sigma bond. Notice that in this step, the arrow starts with lone pairs on CN minus and ends with the carbon. And notice that at this stage, you can interpret this step of the reaction with a HOMO attacks LUMO, where the HOMO on the nucleophile is non-bonding lone pairs on the carbon, and the LUMO is the empty 2p orbital on the carbocation. All right, clear as mud. Any clarifying questions you want to ask? Okay. Similarly, if we were to draw the transition state for the SN2 reaction, we would show the nucleophile coming in and attacking the carbon at the same time as we show the iodide leaving, with a partial negative charge on the iodide to indicate that the bond isn't totally broken, and a partial negative charge on our nucleophile to indicate that the bond isn't totally formed. This would be our transition state structure. Incidentally, we show the nucleophile coming in from the opposite side as where the iodide is leaving. Potential explanation for that is just electron-electron repulsion. You want the negatively charged things in the transition state as far apart as possible. There's another explanation for that we'll get to in just a second. Notice that if the nucleophile comes in at about the same rate that the iodide leaves, the carbon in the transition state is roughly sp2 hybridized and kind of flat. Only unlike the carbocation, there is no empty orbital on that carbon because you're breaking one bond and making another one at the same time. If you were to show this mechanism, what happens in this mechanism, we would show the lone pair electrons from the cyanide attacking the carbon that's bonded to the iodide at the same time as the carbon-iodide bond was breaking. And this would be the product that we would get with the leaving group having left. We can understand this reaction from a HOMO-LUMO perspective. Again, the HOMO of the nucleophile is the non-bonding lone pairs on the carbon. The LUMO of the electrophile would be the carbon iodide sigma star. And if we draw what that carbon iodide sigma star looks like, what we would see is that there is a large lobe on the carbon, a node between carbon and iodide, and another large lobe on the iodide pointing away from the space between the two nuclei. I'm going to use color here simply to illustrate places where the sign of this wave function changes. We've said that the nucleophile attacks from the opposite side of the molecule as the iodide leaves. One explanation, again, is to keep the partial negative charges in that transition state as far apart as possible. The other explanation is that that's where the LUMO is on carbon. It's in the space 180 degrees away from the carbon iodide bond, and we call this backside attack. And HOMO attacks LUMO. You dump electron density into an antibonding orbital. You break the corresponding bond. Now, notice that LUMO is on both carbon and iodide. And some have asked in the past, why don't I attack on the iodide instead? And the answer to that really has to do with the stability of the products. So I don't want to belabor the point, but if you attack at the carbon, you get a strong carbon-carbon bond, and you get I minus, which is the conjugate base of HI, which has a pKa of like minus 11. In contrast, if you attacked with the nucleophile on the iodide, you would make a much weaker carbon iodide bond, and then you would make a carbanion, methyl anion, conjugate base of methane, which has a pKa of 40. So that option, though it may seem reasonable to you, attacking at the iodide, is thermodynamically, not sure how we spell that, exceedingly improbable. Okay, so in general, when doing substitution reactions, you will attack the LUMO on the atom that allows electrons to leave in a more stable way. Right? I minus is much more stable than CH3 minus. All right, questions there? So those are our two options that we've considered. And I want to deal with this issue of how do you know what happens? We said that in the particular example that we chose, this is what we observe for the reaction of methyl iodide with Cn minus. And the reason that I said this happens is because the transition state for the SN2 mechanism is lower in energy than the transition state for the SN1 mechanism. All right, so we're going to try to understand how to think our way through that and when and how experimental circumstances might change the relative heights of the transition states for the SN2 versus the SN1 mechanism. So to do this is going to require a little bit of three-dimensional thinking, and unfortunately my drawing skills are not that good. So I want to present the idea of a three-dimensional potential energy landscape, an energy landscape, a mountain range, where we're going to connect starting materials and intermediates and transition states. All right? So let's imagine, this is going to be tough. We need a three-dimensional axis system. On the z-axis, I guess, we'll put energy. On this horizontal axis, I don't know whether it's y or x, nor do I care. We're going to put formation of the bond between carbon and the nucleophile. And then on the other horizontal axis, we're going to put formation, or rather, sorry, breaking of the carbon iodide sigma bond. And I'm going to briefly copy our summary of our reaction mechanism possibilities. And then we're going to try to plot them on this energy diagram. And shrink those down, drag them over here. Now we can see everything. All right. So let's not worry about energy, but right now let's just consider these two horizontal axes. Pathway 1, make the carbon-carbon bond first, and then break the carbon iodide bond. If I start here before the reaction is over, and I end here, and at this point the reaction is done. Let's say we've got 100% here, 100% formation here, 100% formation there. If I wanted to make the carbon-carbon bond first and then break the carbon iodide bond, tell me which way I should go first on this on this potential energy surface. Starting here, where would I go to break the to make the carbon-carbon bond first? Be to the right, and only then I would go here, right? So we're using orange for that pathway. All right, and this was our so-called option number 1, which we didn't like because we didn't like the idea of the intermediate we would encounter at this corner where a carbon was bonded to 5 things, right? Another way of saying that we didn't like that intermediate is it was probably way too high in energy to be reasonable. Okay, what about option 2? Option 2, we'll use some other color. Let's use purple for option 2. We're going to break the carbon iodide bond first and then make the new carbon-carbon bond. So I'm going to use purple. Where should I draw my purple line? Sort of down and outward towards here first, then there. And at this corner of 100% breaking of the carbon iodide bond, I would have the carbocation intermediate, this methyl carbocation, okay? And so going from my starting point, breaking the carbon iodide bond first and then making the new carbon nucleophile bond, this is my SN1 pathway, okay? Now, what about, let's use blue? Sure. What about the SN2 pathway where I do both at the same time? What would that trajectory look like just on these 2 lower axes? Diagonal, right? We break the bond at the same time as we form the new bond. So this would be sort of our SN2 pathway. And then over here, we'd have SN1 pathway. And then in orange, we have the yuck pathway that we just don't like because the 5-coordinate carbon intermediate there in that upper right-hand corner is too high in energy. All right, so you've got a couple of different pathways that you can take. Now we need to consider what the relative energies of those pathways are, okay? But before we move on, because we're going to make it worse by throwing energy into the mix, I want to make sure you understand what we're talking about on these horizontal X and Y axes, right? One is making the new carbon bond, the other is breaking the old carbon iodide bond. Any questions so far you want to ask? I'm going to erase the yuck pathway because we ruled it out. All right, so with that in mind, we're now going to consider how energy varies on this z-axis as we traverse one pathway versus the other. And this is where we're going to have to squint and sort of look at it sideways and try to imagine three dimensions. So let's suppose that our starting materials are at this energy level, okay? And then since we know our products are downhill, we'll put the products there, all right? the transition state, or rather the pathway along the SN2 reaction, you have to imagine what I'm going to draw as lying along this line. Okay, ish. Maybe we'll use that to connect it to the line below. This would be our transition state. And just to remind you what that transition state looks like, maybe we'll copy it here and then shrink it down there. And then we'll shrink it again. All right, that's what the transition state looks like. Starting materials are the same in both cases, right? It's CH3I and Cn minus, and then products include I minus and CH3Cn. Okay. Now let's draw the SN2, or I'm sorry, the SN1 pathway. That's going to start from the very same starting materials. And what I draw is going to be first along this line and then that line. So I guess I will use purple. And I'm not sure where I want the starting materials to be, so I'm going to move them out of the way for a minute. All right, so we said that going from starting materials to the carbocationic intermediate ought to be uphill in energy. So I'm going to put the position of our carbocationic intermediate there, kind of uphill. And we'll actually move it there so we can see what it looks like. There's going to be a transition state leading to that carbocationic intermediate. And again, if this is difficult to see, you just got to imagine that this point hovers over the corner, the lower left corner in our horizontal plane. So as we go from starting material to that carbocationic intermediate, we're going to go through transition state 1. And this is the transition state of our rate determining step. When we go to print this out someday, we'll be cut off, so I'm going to just slide it down. All right. And that's kind of maybe a little unclear, though we'll try to illustrate it from that perspective. Sort of okay. All right. Then, once we get to that high energy carbocationic intermediate, we can start to make, what the heck happened there? Did you guys see that happen? I didn't see it happen. I'm sorry. If I apologize to it, is it gonna, okay, there we go. Man, thank goodness for the undo key, right? This gives me a chance to maybe improve a little bit on, I'm tempting fate, but no, I think it was fine where it is. All right, so here's your transition state of the rate determining step. And then going from here, we would increase energy slightly, and then it would be downhill to our products. So that's horribly messy and awful. So what we're going to do to try to convey the process here is to draw that one first. And then I think that just made it even worse. So maybe we'll get rid of those vertical lines for the purple one, maybe. I don't know. But not that far. Is there a redo? Okay. So you can see this two-dimensional energy landscape, the three-dimensional energy landscape we've drawn, where for starting materials, we have the option of making the new bond and breaking the old bond at the same time, or we have the option of breaking the old bond first and then making the new bond. Now, because I told you that these starting materials prefer the SN1 pathway, what we've drawn for this energy diagram is consistent with that. The transition state leading to the SN1 pathway is much higher in energy than the transition state leading to the SN2 pathway, so it's just easier to go through the SN2 mechanism. I guess for completeness, maybe we ought to take a picture of the transition state for that rate determining step, and we'll just paste it there and shrink it down and shrink it again so we can see that's what it looks like. Okay? So that's the picture we've got now. Now, the question we want to ask is, if we change the structures of the starting materials, how does that change the relative heights of transition state 1 for the SN1 pathway versus just the regular transition state for the SN2 pathway? Okay. And I think Caroline at home is asking sort of this question, what do we know about the relative heights here, about how easy it is to go to the carbocationic intermediate versus go over there? And we're going to talk about things that will vary the height of the blue transition state versus things that will vary the height of both the purple transition state 1 and the carbocationic intermediate. Okay? So that's where we're going to go next. But before we do, any questions about this horrific drawing? No? Okay. All right. So what could change the height of the transition state that's in blue? The blue transition state gets progressively higher in energy as we go from primary to secondary to tertiary alkyl halides. And the reason for this has to do with the requirement in the SN2 reaction for backside attack. So for a primary alkyl halide, well, with the example you've seen so far was with the methyl halide and a nucleophile that comes in from the backside. For the methyl halide, it's quite easy because what it faces on that back side are just protons. But as we progressively replace those protons with alkyl groups, so what I will draw now, we're just going to replace one of those, say, with a methyl group. Now there's some steric hindrance. And so if we were to plot here for methyl versus primary alkyl halides, if you want, we could either plot the height of the transition state in blue, or we could just call this rate of SN2 reaction. The rate of SN2 is fastest for the methyl halides. It's still fast for a primary alkyl halide, Secondary alkyl halide is going to look the same, only now we're going to have two non-hydrogen things attached to the alkyl halide carbon. That's two larger things that get in the way. And so the rate of SN2 will be slower here. And we'll see that by the time we replace all three groups on that carbon that bears the halide, by the time we replace all three hydrogens with alkyl groups, the reaction no longer happens. No SN2, and that is because the transition state is too high in energy. The nucleophile can't get in there to attack the carbon because the alkyl groups on the backside are in the way. They just block the approach. Yeah?
So the one that we dealt with was the step one, the fast one?
Yeah. We didn't do all three, yeah. What is shown here, what is illustrated here was for the methyl halide, and that's why we're showing that transition state as being pretty easy to get over.
Primary, right?
Yeah, for methyl or for primary. If we were to start increasing the amount of alkyl groups on this carbon, we would see this transition state start to increase in energy, making it slower to get over that barrier. Go ahead.
So in terms of like the tertiary one, would you have to go through a different mechanism? Get rid of the halide bond first?
Right. So the question here in class is, if the transition state for the tertiary alkyl halide is too high in energy to go through, then maybe the only other option you've got is for the leaving group to leave first to do the SN1 mechanism and then go there. The blue pathway is the one that's preferred in this case for the methyl halide. Yeah, if I said that wrong, I'm sorry. For methyl primary alkyl halides, the transition state for the SN2 reaction is low enough in energy that it is fast. The blue pathway is fast and preferred. For secondary alkyl halides, it turns out we will see the heights of these barriers are comparable. No, I misspoke. Hold on. Hold that thought, because there's more going on there. For secondary alkyl halides, the transition state through SN2 is a little bit slower, but still possible. For tertiary alkyl halides, it gets so high that SN2 isn't an option anymore. Go ahead.
So if you're to replace any of those three hydrogens, like the tertiary, but with a single atom, like boron, and maybe its connected hydrogens, will that also stop it? Or is it just
That's an interesting question. I can't think of anything other than carbons that you might put here that would not also change the chemistry of the reaction. If you put another heteroatom here attached to the same carbon that has the iodide, that will no longer be like a regular alkyl halide. That'll do something else entirely. Yeah, go ahead.
The first option that we omitted, where you have like the 5 different things bonded to it,
Yeah.
Would that ever be more favorable than like a 2 or 3 degree carbon thing like you're drawing out?
So option 1, will that ever be more favorable versus SN2? The blue pathway, I think. No, because actually the steric problems that the SN2 transition state has will get even worse if you try to make 5 things bonded to that carbon and make these bonds both short. So sterics actually will make the orange pathway that we didn't even draw even worse. Yeah. Okay, so how does more steric hindrance make the transition state higher in energy? It just has to do with electron-electron repulsion. As the nucleophile approaches, it has to go from what the starting material looked like, which is all of those substituents on that carbon facing this way. And as the nucleophile approaches, it's got to push those groups out of the way. And that gets harder and harder to do, the larger these groups are. So increasing the size of the groups attached to this carbon increases the amount of electron-electron repulsion that the nucleophile has to overcome as it attacks that carbon. The other way to think of it is, as Wallace is noting on the chat, in order to attack that carbon, you have to get access to the sigma star, and alkyl substituents start to get in the way of that and block that approach. To illustrate that, it might be useful to go to the Spartan program. Here is a methyl bromide. The sigma star there is quite accessible. Now let's go back to, and let's add 3 methyl groups. And now let's, molecules not, of course it's not in the database, come on. Well, what if we did that? Are you in the database now? Yes. Now, I want you to ignore for the fact that some of the LUMO is on those adjacent hydrogens. We'll get to that when we start to talk about elimination chemistry. It has to do with hyperconjugation. But this is the LUMO, you can see, is now sort of blocked by the presence of those methyl groups. And if we make a space-filling model, you can see how it gets very, very difficult to attack that central carbon, which is labeled, because the methyl groups get in the way. All right. This is the Spartan app, by the way. Okay. Other questions? So we've talked about how the alkyl halide structure can influence the height of this blue transition state. But remember, the rate of the SN2 reaction depends also on the identity of the nucleophile. So the starting material gets higher in energy as the nucleophile gets more reactive, as we increase the reactivity of the nucleophile. Looking at our energy diagram, what is going to happen if the starting material increases in energy? That means we get over that barrier faster, right? If we assume the barrier stays more or less in the same place, if we increase the energy of the starting material, that should accelerate the reaction. So one other way we can accelerate the SN2 pathway is to use better nucleophiles. So we need to talk about what makes a good nucleophile good. Nucleophile reactivity is related to the fact that we have a high energy, highest occupied molecular orbital. Generally, for substitution reactions, we're looking at lone pairs. And we can use our pKa intuition to a point for identifying good nucleophiles. Good nucleophiles are, well, good nucleophiles generally have conjugate acids with pKa's that are greater than 0. So this includes, if we think about, and I'm going to start from sort of the lower end of that spectrum, the acetate anion is conjugate base of acetic acid whose pKa is like 4. Another group that tends to show up in this range is negatively charged sulfurs, or what are called thiolates. These are conjugate bases of thiols whose pKa's are around 6. Cn minus is the conjugate base of HCN. HCN smells like almonds and it is deadly. So in the lab, when working with cyanide, if you smell almonds, you need to run. The pKa there is around 9. Azide is an interesting nucleophile that comes up here and there. It's often just written N3 minus. HN3 has a pKa of around 9. Amino compounds like ammonia or a primary amine. I believe you guys corrected me. The ammonium, just NH4 plus, has a pKa of around 9 as well. Primary amines have pKa's that are around 11. Hydroxide and alkoxides have conjugate acids, water, and alcohols whose pKa's are around 16. So we might actually continue on. One of the best nucleophiles that we'll use in this chapter will be the conjugate base of a terminal alkyne whose pKa is around 25. So the lower the pKa, the more stable the conjugate base is. But we're going to see that all of these are decent nucleophiles. Okay? We're going to worry later on as we get to chapter 8 about the extent to which these good nucleophiles might also be good bases. Just as a preview, the difference for our purposes in this chapter between a base and a nucleophile is the nucleophile attacks the LUMO at carbon. A base can attack the LUMO at a nearby proton, but we'll discuss that later. Anyway, if you use a stronger nucleophile, you can promote the SN2 reaction pathway. All right. You can't promote the SN1 reaction pathway with a good nucleophile because the nucleophile isn't even involved in the first step, right? Okay. Question so far about how we can make SN2 more favorable. All this is theoretical at this point. We're going to get to some examples soon. So let's actually do a few examples. If this is my nucleophile and this is my electrophile, what do I predict is going to happen there? Is SN2 a possibility? Based on what we've talked about? Okay, some of you are saying yes, probably because the nucleophile is good. You're right that the nucleophile is good, but there's something else. What is that something else? The alkyl halide, right? Steric hindrance makes the transition state for the SN2 reaction way too high in energy to be viable. So we would say here, no SN2. What's going to happen? Well, SN1 is one of the possibilities. And it turns out that it's difficult to teach chapter 7 and 8 in a way that separates substitution reactions from elimination reactions. Because as a preview, we're going to see that once you make this intermediate, the carbocation, in addition to substitution, there's another branching pathway that pops off of there that happens all the time also. So we need a 4-dimensional potential energy landscape, and that's, though my son Nate likes to think about those kinds of things, I've not yet figured out how to draw something like that. So we'll just have to talk our way through it. What would I have to do here? What could I change to make the SN2 pathway more favorable? Yeah, so if we go down to the methyl halide or something that's less substituted, then that becomes a possibility. All right. As we go on, we're going to need to talk about ways to change the energy of this transition state and this intermediate. We're going to be talking a lot about the stability of a carbocation. We're going to actually see that carbocation stability follows this trend but backwards. Methyl carbocations are less stable than primary, which are less stable than secondary, which are less stable than tertiary. And we'll talk about why. But one important feature of this discussion will be that the energy of this transition state and this intermediate are closely tied together. Their structures are actually pretty similar. And we're going to see that what makes the intermediate more stable will also make this transition state more stable. So just as a preview, the very same thing that's going to make this the blue transition state go way up in energy is going to lower the energy of the intermediate in this transition state. So we'll see that tertiary alkyl halides can do the SN1 pathway for reasons that we'll talk about next time. If you're overwhelmed, that's good. That's exactly where you should be. We'll try to fix some of that before the exam. All right, we'll see you next time. Colin at home, is study guide 6 still due tomorrow? Yes, we are in chapter 7 and 8 now. Chapter 7 and 8 won't be due till after the exam.